All right, today's lesson, pretty simple. Going back to power rule again. Let's recap. What is the power rule? Which is to help you find the derivative again. What is the power rule? Oh, it is there too. Sorry. Yeah, it is right there. That is the power rule. This is your power rule, and I'm just going to change the thickness. This is your power rule. What does the power rule tell you? There's only 1, 2, 3, 4, 5, 6 of us. So I'm going to pick each and every one of you every time I ask a question.
And then 2 people. What? And you want 2 people by the end of the year?
Yeah, I'm getting there. I'm getting really close, actually. This is good. Power rule. What is this? Once you find you do this whole formula, what does this tell us? What's the point of doing a power rule? Gradient function. So I'm going to write here, this is the gradient function. But then some of us still don't understand, what is a gradient function? So I find the derivative, say, here's an example. I'm just going to do an example so you can relate to it. If I told you f of x, so the function that you have is a simple quadratic graph, x squared. Then we find the derivative. Now, according to the rule, it is whatever n is. So the n is the power. So the power is 2. Then according to the rule, it's n, which is 2 times 2 minus 1, right? So here we go. I'm going to write it. 2 times x to the power of 2 minus 1, which is 1. So this is my derivative. Great. This is apparently the gradient function. What does that tell me, though? Why do I want to find the gradient function? Ollie.
Because it tells you the gradient of that particular point on the equation.
Very good. I like that. Okay, so for those who didn't understand, I'm going to illustrate this point. So we can see that a quadratic graph, a simple one, this is what it looks like. That's what a y equals to x squared graph looks like, right? Now at each point on that graph, there is a unique tangent line. So tangent line looks something like this, a straight line that touches that point only once. So I've drawn that. When it touches that point, this is the point where whatever x is, so let's say x is 1, hypothetically. And this is y value, so if it's 1, actually I'll make it 2, so that y equals to x squared will tell us this is 4. Okay, so this coordinate here is when x is 2, 2 squared gives you 4, right? According to this rule, what's the 2x tell you? It tells you that any random point you choose on this curve, doesn't matter which one, whether it's x equals 2, x equals 1, x equals 0, it will tell you the gradient of that tangent line. So the tangent line is a green line. It's a straight line. It is y equals mx plus c. All it tells you, so this gradient function, when I say what is a gradient function, it's just the rule that helps you find m at any point. So depending on which point you're looking at. So in this case, I'm talking about x equals 2. Then if I want to know what is the gradient of this line, so this line is y equals to mx plus c. If I want to know what is the gradient of this line at x equals 2, well, according to my rule here, I'm finding the derivative when x is 2. So 2 times the 2 gives me 4. So what that tells me is I now know gradient is 4. That's it. So it's a gradient function because you can pick any point and this rule will help you find the gradient. That's why we call it gradient function. So that should then help you understand, if you really understand that theory that I just described, the whole derivatives and first principles is to help you find the gradient with only one point. Notice that there was only one point in this question. Normally, gradients require 2. This question here, example 13, I've done the example, but I haven't made a video for it. So this is for exercise 17B. Let's have a look. If we understand the idea, then you should be able to answer this question now by applying your understanding. They tell you, for each of the following curves, find the coordinates of the points on the curve at which the gradient of a tangent line at the point has the given value. See, when students read that, they're like, I don't know what that question's asking. Okay? And that's what I'm saying. If you can picture it, all they're trying to tell you at the moment is you have y equals x cubed. So picture it. When you're doing these kind of problems, I want you to picture what you have. That's what methods is all about. It's about picturing what you have. So you currently have a cubic graph. Hopefully you know your cubic graphs by now. So this is what a cubic graph looks like. Y equals x cubed. All they're telling you is find the coordinate. So where on this graph, okay, so I just picked a random point. Where on this graph where when you draw the tangent line, so I'm going to draw a tangent line. Here we go. That's a tangent line at that point. Find the coordinates. That's what they're saying. Find the coordinates. So this coordinate here, x, y, find the coordinates if we know that this is going to be 8x or 8. The gradient is going to be 8. That's all they're telling you. So if you draw it out, this becomes somewhat more digestible in the sense that all you're doing is they're just telling you the gradient of that line is 8. What is that point? That's your job. So you need to find x and y. Hopefully in this chapter, and as you understand, as you're going from chapter 17, 18, and then 20, anytime they ever ask you about a gradient of a tangent line or at one point, you should be thinking of derivatives. That's why you learn all these rules, right? So here we can link back, well, actually 8, I can find 8 because I know m, which is the gradient, is the same thing as finding the derivative of your function at that particular point. So in this case, I don't know what this point is. I'm going to call it A. Okay, I'm going to call it A. It's a value. So at x equals A. That's essentially what they're telling you to do. So I know m is 8 because that's what they told us. Gradient is 8. Do I know the derivative? Well, I have the function. And that's why you use your power rule and your skills to, instead of doing the first principles, we do the shortcut. We say, well, actually, yeah, I can find that out. If y is equal to x cubed, using your power rule now, what is the derivative equal to? Yeah. Okay, so we're just doing 3, which is the n power, x to the power 3 minus 1, 2, 3x squared. So here, I now have the variable x because this tells me when I'm going to get the answer of 8. Okay, that tells me this x value. That's what it's telling me. I want to know when x equals to a, so all I'm doing is I'm substituting a in, and this is what I get. I get 8 is equal to 3 times a squared. Solve for a, because if I can solve for a, I know that x coordinate point. That's all it is. So here we go. Divide 3 on both sides, you get 8 over 3 equals to a squared. To get a, inverse of squaring, square root. Here we go, I get 8 over 3, square root gives you plus or minus. Okay, so I get 2 values of a, that can give me a gradient of 8. And how does that make sense? Well, logically, if you look at that graph, it kind of makes sense that there must be another point somewhere where I can probably get a parallel line, where these two are parallel, and I get the same gradients. That's why you have 2 points, if you understand it visually. Okay, so that's what I'm saying. You can actually just work on it mathematically, or you can try to understand it in a visual aspect. That's what I want you to take out of it. Okay, so today's lesson, you'll be doing the same thing. So when they say find coordinates, you found A, which is the X value. How do you find Y? Sub it back into this equation, and you get the Y value. Yep.
Is there like a plus minus plus or something? Because like with like quintics, wouldn't there be like more than 2 values for like a thing?
Quintics.
It's like,
Oh, yeah, you can. You can. Very good question.
like,
Yeah, that's possible.
it'd only be a plus minus, so like we miss out on some of the other ones. How would you like?
No, but quintic, it would have been A to the power of 5. So if you had 1, 2, 3, 4, 5, then when you fifth root it, there should be multiple answers that could have given you that. So yeah, if you can get, say, if it happens to be that you can get, say, 3 parallel lines, yeah, you would possibly have to factorize this, and you would get 1, 2, 3, 4, or 5 brackets to solve. But yeah, you're right. You can have multiple answers. In our case, because it's a square, you can just change it to square root it. But in this case, likely, you're going to have to factorize it. And that's why at the start of the year, factorizing was important. You have to be able to do quadratics and cubics, because if you can do quadratics and cubics, then you can do quintics. But that is a very good question. You would be encountering problems like that later on. That's true. Not this year, probably next year. Okay. All right. So today's lesson, what are you doing? You are doing exactly the same things, except this time in exercise 17C, they're now saying you can also apply when it's a negative power. Okay. So as long as it's we said initially it's x to the power of n, and n was like 1, 2, 3, 4, but we didn't talk about whether it could be negatives. In this case, yes, you can. That's what exercise 17C is. So as an example, here we go. If y is equal to x to the power of 4 minus 2 times x to the power of negative 3 plus x to the power of negative 1 plus 2, where x cannot be 0, using your rule. So here we go. I'm going to show you the rule again. So f of x, if it's equal to x to the power of n, then the derivative is n times x to the power of n minus 1. So I'm going to use the rule. Here we go. We're going to use the rule. Delta y, delta x. Okay, so you don't have to do f of x and f dash of x unless you want to. That's function notation. This is Leibniz notation. So here we go. N is 4 for the first one. So the first one is n is 4. So I'm just doing 4x to the power of 3. Whoops, that was a different color there. Let me just do that again. There we go. And the next one, negative 2 stays as it is. All we're differentiating is the x to the power of negative 3. So here we go. That is now going to be times derivative of x to the power of negative 3. N is negative 3. X to the power of negative 3 minus 1 is negative 4. That's the only thing. Okay, so you're still using the power rule. It's minus 1. And again, plus, this is now negative 1 times x to the power of negative 2. And hopefully you know that is still 0. Okay, and that gives you your final answers: 4x cubed plus 6x to the power of negative 4 minus x to the power of negative 2. Don't leave your answers with negative powers. Like I always say, next year you want to be writing them with positive powers. So your final answer should be 4x cubed plus 6 on x to the power of 4 minus 1 on x squared. That's your delta y, delta x. Okay? And that's it for today's lesson. Yep.
Is that still technically a polynomial?
Correct.
But if there was no positive power, then you can't do that.
If there was no...
Is it still a polynomial if it's all negative powers?
Oh, is that what you were asking? It is traditionally no. Traditionally no. It's still classified under polynomials, but in your power rule, they specifically talk about in the proof, they only worked it with positive powers.
So it has to have at least one positive power for you to be able to do the power?
No, it can be all negative. Yeah.
It can be all negative.
Yeah. So that's it for today's lesson. That's exercise 17C. That's introducing to working with the same problems, and you'll find that the difference between it is students will find these types of problems look scary, but it's actually the same thing that you've been doing with what you've been doing deriving over here. Okay, now, exercise 17C, back then we used to do first principles, so then you would do these questions by first principles. You do not need to. So don't do questions with first principles, ignore them, and just go right to, say, question 2, where you're practicing to find the derivatives, okay, without the first principles. In terms of how do you do these types of questions using power rule, you'd have to actually use chain rule, but I haven't taught you chain rule yet, so that's why anything with a fraction like this, just ignore, except for these ones. Anyone know how would you do? So these ones you should be able to do. How would you do this type of problem? Because I'll tell you the common mistake that most students do once they finally catch up to where I'm up to. So if I'm teaching 17C, most students are still on 16C or so.
When you just like put the fraction all into like one line instead of like having a denominator, and then do the same rule.
Very good.
All of them numerator by z to the base.
Very good. This one's breaking it up into their terms. What students normally do as a mistake, this is what they normally do. They will differentiate the numerator by itself. So they'll do, that will be 3 times 2z plus 2 plus 0. And then they'll differentiate the bottom and they'll say that's 2z. Wrong. You can't do that. Remember, the rule was only if you had x to the power of n. They never talked about that you can differentiate the numerator of a fraction. They never said that. They only said it's individual terms. It's a variable to the power of something. So this here is one massive fraction. You have to separate them. So like Matt and Andre just said just then, you can split this into 3z squared over z squared plus 2z over z squared and then plus 4 over z squared. Now you've broken them up into individual terms. You can simplify them. Z squared divided by z squared cancels out. So you get 3 plus z divided by z squared gives you 2 over z and then plus 4 over z squared. Now you may still feel like, well, apparently we can't differentiate fractions. True. But we can write z in the denominator and bring it up using index laws. We know that's the same thing as writing 2z to the power of negative 1. Okay, so that's 2 times the z to the power of negative 1. This is still 3. And then here, this is plus 4z to the power of negative 2. Then you can use power rule now. See, that's power rule. One variable, n is negative 2. Variable z, n is negative 1. Okay, so that's the only part. And that's how I know whether students have done their work. If I gave them a problem like this and I would see whether they can do something like that, I know straight away that they only can do power rule for exercise 17b and they may not have done 17c yet. That's how I tell. Okay, Andre.
I was thinking when you just change the z squared on the bottom straight from the start to z to the minus 2, and then you have like a factorization. So the times that whole thing up the top.
Oh yeah, that's great. Yeah, that's another method as well. So for those who are trying to picture what Andre's saying, you've got 3z squared. Why does it keep moving? You've got 3z squared plus 2z plus 4. What he's saying is, if you bring the denominator up straight away, then that now becomes z to the power of negative 2, and it's being multiplied. So you can expand it by multiplying these. Okay, and if you multiply it, you know, index laws would then be z squared 2 plus the negative 2 plus 2 times z to the power of 1 times, 1 plus negative 2. And then the other one is plus 4 to the power of z negative 2. There you go, and you get the same answer. Okay, so that's another way to do it too. It's very good. It's true. Yeah. So that's about it. I feel like that's generally what they'll play around with for C. Later on, as you learn more techniques, then they'll start embedding other things with like brackets and functions. But at the moment, you only know power rule, and your skill is next term, I'm going to develop your derivative rules and derivative skills. And don't forget, the purpose is just to simply find the gradient of a tangent line at any single point on the curve. Okay? All right, that's 18 minutes of me explaining, and we're going to stop the video here.